Not only can we make tables out of continuous data, but we can also make histograms out of it. So the following histogram shows the age of operating nuclear reactors in the US as of 2025. Yes, it's real data. So this is the real age of nuclear reactors in the US. So we can see the age is down here. This is quantitative data, but it's also been put into bins. So when it asks you what type of graph is this, this isn't a bar chart, right? The bars are touching. This is a histogram. And then we look over here and we can see that it says frequency over here. So that means that this is a frequency histogram. The bars are touching. This is quantitative data. Pareto charts and bar charts are not quantitative data. They're qualitative data. These two are quantitative data. So we'll have numbers on our x-axis. So I'll just put that numbers on the x-axis. Okay, so what is N? Well, there's 2 nuclear reactors at this age group, 1 nuclear reactor at this age group, and so on. So how many are there altogether would be little n. And I used Desmos and I added them up, and I got 94. So there are 94 nuclear reactors in the US. Oh, and actually this is a typo, I would say. I don't think this is lowercase n. I think this is capital N, because this is a population. This is all there is in the US. If you want to think of the US as a sample of all the countries, that's a different story. But I would argue this is capital N. This is a population, right? We would treat all the nuclear reactors in the US as their own population because, of course, each country has its own rules and regulations regarding nuclear reactors. I mean, we can make those comparisons, but it would be very common to just be interested in our own country and be interested in our own nuclear reactors. So I'm going to actually change this. This is a population. All right, now the tallest bar has a value of 26 on top. What does this mean in the context of the situation? So let's go here and let's look. So the tallest bar is 26, which is right over here. And you can see that it starts at 50, and these are years. And this is 60, so this number in here must be 55, right? So this is 45 and so on. This is 5. So what's happening is the class, there's 26 reactors age 50 to, not 55, 55 is the start of the next bar. It's actually 54.9, right? Or 54. So we could say, now it's the tallest bar. So the fact that it's the tallest says the most common, that's why it's the tallest, age of a U.S. nuclear reactor is, I guess I could just say, is 20 to, or is 50 to 54.9 years old with 26 reactors that age. Oops, sorry, that's off screen. There we go. All right, now how many reactors in the US are 45 or older? Again, notice that's a how many question, so that's going to be a frequency question, where we're going to add up frequencies. So we're going to start with the frequencies of 45, which is right here. We start there and we start adding. So we add the 14 and the 26, so that makes 40, plus 4 makes 44. So I'll make a little note. 14 plus 26 plus 4 makes 44 reactors in total that are that age. What percent of US nuclear reactors were less than 40? Okay, less than 40. 40 is right here. So less than 40 is all of these ones. So we would add up, first of all, how many there are. 1, 2, 3, 4, 5 plus 25 makes 30. So there's 30 reactors that are below 40 years old, because 40 starts right here. This bar right here is the 40 to 44-year-olds, right? 45 is actually the start of the next bar. I guess I should mention, these numbers that we see here are lower class limits, right? We're seeing the low edge, right? The first number in a class. So the first number for this class is 0, the next number for this class is 5, and so on. Okay, so we want to add all those up. So 2 plus 1 plus 1 plus 1 plus 25, all divided by the total of 94. So that's 30 divided by 94. That's the fraction. So now we're going to go get a decimal for it. And we get 0.31914, or 0.319. And we want one decimal place on the percent, right? Because it's asking a percent question, right? So we're going to have to do relative frequencies. So we're going to have to divide this, which we did, and that would make it 31.9%, right? From fraction to decimal to percent. All right, now what is the shape of this distribution? Remember that the skew goes with the few, right? So the skew goes with the tail. And this very obviously has a left tail, right? So there's a clump over here without them, and then left tail. So this is very much skewed left, right? It has a tail to the left, right? The tail is what determines the skew. Now, explain why we do not know how many reactors are 47 years old from this graph. Okay, so let's look. So we know there are 14 reactors between 45 and 49, right? Because 50 is the start of the next group. So we know there's 14 reactors there, but we don't know how many they are specifically at any particular age because they're put into a bin. They're put into a group, right? Because they're grouped or binned, we don't know what any individual values are. All right, I'm going to write that up. Okay, what I just said. Right, we know there are 14 reactors aged 45 to 49.9, but because the values are in groups bins, right, they're grouped and binned, we do not know the frequencies for any particular values. That's the downside to histograms. Histograms are great, but they do put things into bins, and sometimes those bins can make it hard to know any particulars of what's going on.